So we're going to look at some graphs of a derivative, and we are going to sketch a graph of f of x. Like, what does the first function look like without taking the derivative? Okay, and again, it's a sketch, so it's not exactly what it is, but it could be a possible solution to it, if that makes sense. And then to help us with that, we're going to kind of write underneath in the analysis box there, like, what helped us get that picture of f of x, okay? So if I look at the graph for this first one, we're going to start out pretty easy and work our way up. Okay, this first one here, this is the derivative function on the left. Okay, this derivative function is a horizontal line. It's a straight horizontal line, which means that the derivative is equal to what at every single value here?
2.
This is 2, right? So my derivative is 2, right, for that entire function. So think about that. If your derivative is 2 for an entire function, what is that function going to have to look like?
A linear line.
It's a line, right? It's a straight line, okay? So when we're kind of thinking about the analysis of it, we could say something like our derivative is equal to 2, so we know our slope of f of x is equal to 2. So in my possible graph, it does not matter where it is, as long as I have a slope of 2, up 2 over 1, down 2 over 1. Okay? And I could draw a straight line there. Now, I could have drawn that any other place. I could have drawn it up, to the right, down. As long as it has a slope of 2, this graph would give me a derivative graph that looks like this. We okay so far? Okay. Next one here. This derivative function, again, is a straight line, right? But technically, remember, all of these values are slopes. So that's saying at -1, -1, there is a slope of this value. At -2, there is a slope of this value, right? So we need to identify what is a possible f of x graph look like. To help us, we can look at where is our derivative negative, where is our derivative positive. So if you look at this graph, our derivative is negative everywhere below the x-axis. So everything from -infinity to 0 is a negative, everything to the left of 0 has a negative derivative, right? Everything to the right is going to be a positive derivative, right? It's above the x-axis. So those two pieces of information tell us something about our graph. If we know that f of x is less than 0, what does that mean about our graph?
The slope is negative.
What does it tell us about our function? Yeah, our function is decreasing, right? F of x is decreasing. Specifically on the interval from -infinity to 0. Okay, it's going to be positive where f of x is increasing on the interval from 0 to infinity. Okay, so we know where it's increasing and decreasing. But the other thing that we need to think about is, could I take the derivative of this function again? Yeah, what's the derivative of this line? It's going to be one number, right? I don't know, it's like up 1 over 1 it looks like. So yeah, the derivative of this is 1, right? So if I looked at the second derivative tells us if it's going to be concave up or concave down, specifically if it's positive or negative, okay? So if I look here at my second derivative, so f double prime of x, is that greater than 0 for the entire interval? You betcha. So it's greater than 0, meaning that f of x is going to be concave up on the interval from -infinity to infinity. Okay, so now I can go ahead and draw a possible sketch for what this might look like. We know that to the left of 0, it's decreasing for f of x. So I know that it's going down somehow. okay, all the way to 0. And then at 0, it's switching to increasing, right? So my function is increasing to the right of 0. So check mark on both of those. Is it also concave up there from negative infinity to infinity? Yes. Now, could my graph have been like shrunk a little bit or stretched a little bit? Yes, okay? As long as the important part here is that it is at 0, 0, okay? I can't have shifted, or I couldn't have shifted my graph over to the right or to the left. I could have had it go down further. So for example, I could have had my graph go like this and then up, right? Because it's still changing from decreasing to increasing at x equals 0. But again, this is just a possible function f of x. It doesn't give us the exact function, okay? Which also, this should make sense because our function for this would be x squared. And if I took the derivative of x squared, I would get 2x, right? So derivative giving me a slope of 2, or maybe it was actually 1 in this case. But that should look pretty accurate there. Any questions on those first two? Okay, next one. Looking at my derivative. I'm drawing a f of x function. So I need to answer some following questions about what is the derivative telling me about my function. Where is it increasing? Where is it decreasing? And then for my second derivative, it tells me where is it concave up or concave down, okay? So I kind of like to write those out first. I think it helps my brain, and we can also label them on the picture. So our derivative of x is less than 0. Where? Where is it less than 0?
Everywhere.
Everywhere. This whole thing is less than 0, right?
Well, except 4, 0.
Except what?
Except 4, 0.
4, 0?
Like when it's equal to 0.
Oh, yeah, I see. Yes. So it's less than 0 except for when it is touching 0, yes, technically. So it is always going to be decreasing. Now, just like Jacob was saying, at the derivative of this point, right? The derivative of this point would also be 0, right? So we know f prime of x equals 0. We also know that our derivative at 0 would be 0, right? The derivative of this value right here, which means there's either going to have to be, some sort of like maximum or minimum, or another way that we can get a derivative of 0 is when we have kind of that like inflection point thing like that. That's when we have another slope of 0, okay? All right, and then let's see, concave up, concave down. So second derivative. If I look at the second derivative of this function, when is it less than 0? Okay, so when is it less than 0? When is the second derivative less than 0? So let's kind of mark on our graph where our derivatives are. So if I look at the left side here, starting on the bottom left, all of these slopes of these tangent lines are what? Positive, negative, 0. All of these slopes. These are all positive slopes, okay? Positive slopes there, all the way up until we get to this point where my slope would be 0. Then what about all my slopes on the right side? These would all be negative, right? All of these slopes are negative. So our second derivative is less than 0 from 0 to infinity, which means it is concave down on that interval. It is positive or greater than 0 all the way from negative infinity to 0. Concave up. So now I need a dry sketch of what this picture would look like. Okay, I always kind of start with the increasing and decreasing. I know that this is always decreasing. Okay, so if I start, I know that it's always going down. So that's so far a possible option, but is it going to fulfill the rest of those things that we need to have happen? Like concave down on the left side and concave up on the right side. or sorry, not on the right side. It's concave up on the left side because it's negative infinity to 0. And it's concave down on the right side. But this here is just like a straight line, right? So on one of the sides, I need to have concave up. So some sort of, remember, like smiley face looking thing, or concave down being an upside down kind of smiley face thing, or think hill and valleys. It doesn't have to be a full U or upside U, but I need to draw a sketch. So that's exactly right. If I look, because also my second derivative at 0 has to be 0. So I know that it's got to go through this point, and it has to have like either, it has to either touch and go back up to have a slope of 0, or it has to have like a little S-looking curve so that we have kind of that inflection point happening there, okay? So on the left side, from negative infinity to 0, it is concave up. So it looks something like that. But from 0 to infinity, it's concave down. So it's got to have kind of that upside down curve there. Which this point right here, that point is kind of that change in between, right? So it's kind of, that slope at that point is 0 there. So again, this is kind of a possible function of y equals negative x cubed, which means that the derivative would be negative 3x squared, right? Which that makes sense because it's a parabola and it's upside down. Yeah? All right, last one before we do some other kind of practice looking at graphs, answering some questions. We're given a derivative function, and then we're finding a possible f of x function that's going through the point negative 4, 2. So it's telling us specifically it's going through this point negative 4, 2. Has to go through that point. Okay, this one doesn't look as nice, does it? So we've got some more things that we're going to need to look at. So I kind of want you to fill in the blanks here. So I want you to look at when is my function f of x. Oh, maybe go away. There we go. When is f prime of x less than 0? When is it greater than 0? And then I also want you to look at when is your second derivative less than 0 and your second derivative greater than 0. Okay, so list all of these things, because those things tell us when is it decreasing, increasing, or when is it concave up, concave down. Okay, so try that out, and then we'll go over it here in a few minutes. So once we have all this information, I always kind of like to start with the increasing and decreasing information and then double check that we have the concave up, concave down stuff as well, okay? So I'm going to start, it says on the very far left, from negative infinity to negative 4, I'm decreasing, okay? So that means I'm going down all the way until this point. Because I have to go through that point, it said, right? And then at negative 4, what do I switch to? Increasing. So at negative 4 to negative 2, I'm going to increase. So from negative 4 to negative 2, I'm increasing. Okay. And then let's see, at negative 2 to 4, we are decreasing, right? So negative 2 all the way to 4, we are decreasing. So I could go like, oops, that wasn't exactly pretty, but I could go to that point. Or it doesn't mean exactly at like 4, 0. I could go all the way down here if I wanted to, where 4 is down there, if I wanted to. Yeah? Either one is fine. Again, it's a possible graph. And then we go increase at 4 to infinity. So I'm going up to the right at 4. Okay? That's just using my information about increasing and decreasing. Now let's look and see, because these two things are checked off. Those are good, right? Let's double check that our concavity also works for our graph. So it is less than 0 or concave down from -3 to 1. So if we look at our graph, from -3, right here, to 1, it is concave down. Do we agree with that? Yeah, I agree. Okie dokes. And then it is concave up on the intervals -∞ to 3. So right here, we are concave up. That is true. And then from 1 to infinity. So from 1 to infinity. Those are both true, right? Perfect. Again, those are just, this is a possible graph. It could have looked slightly different than what I have here. Okay? All right. Moving on to looking at a graph, answering some questions about relative max, relative min, and that kind of stuff. Okay, so again, we're given a derivative function here, and it's on the domain -3 to 3, and we need to answer the following questions. First one being, on this graph, where is the function f of x increasing? So when is f increasing? If I want to know when f is increasing, but I'm given the derivative function, what am I looking at?
When it's above 0.
When it's above 0, right? This is when the first derivative is greater than 0. Well, it's greater than 0 everywhere above the x-axis, right? So go ahead and write your intervals for that. This is your justification right here. So once you have your intervals, that justification is written there for you. Okay, do we agree with that? Again, at 2 it is 0, so we're not going to include that one because we're looking at when is it greater than 0. And I did not include 0 because, again, it has to be greater than 0. So on those three intervals, I should probably say f of x is increasing because of that reason right there. The first derivative is greater than 0 on those three intervals. Okay, next question's asking about, on this graph, where is f have a relative maximum? Relative maximum, given a first derivative, what am I looking for? Yeah, where it's changing from positive to negative. And obviously, specifically, where is the derivative equal to 0? Those are the points that I'm checking. So this is when, specifically, if it's maximum, which way am I changing? From negative to positive or from positive to negative? Positive to negative, say. So our first derivative changes from positive to negative at
-2.
the given x value. Yeah, so if I go back up to my graph here, it's positive up top, and then it goes negative at this point, 0, right? Or f prime of x is 0 at -2. Do we agree? It's also 0 at 0 and at 2. My derivative is equal to 0 at those three values. So those are the three values you're checking, but that's the only one that goes from positive to negative. This is negative to positive. This is positive, positive. Okay? So the only value where it's going to be a relative maximum is at the point x equals -2. So at x equals -2, f of x has a relative maximum. And again, because my justification is right there. Because the derivative changes from positive to negative at x equals -2. Okay. All right, letter C. We're talking about concavity now. So I'm going to erase these signs. Go ahead and go through your derivative function and mark all of your positives and negatives for your second derivative. I'm going to go ahead and mark on here the second derivative slopes of this graph that I would get. Hopefully our slopes look something similar to this. But specifically, if I'm looking at concave down, I care about when my second derivative is equal, or is less than, I should say, 0. So all of those, which I put in blue, but really it's actually the red values up there. All of my second derivatives that are less than 0 would be from the interval -3 to 0, sorry, to 1, -1, and then from 1 to 2. We could say f of x is concave down. Because of that reason right there. Okay. All right, lastly here, we're looking at when are we going to have an inflection point? Okay, so when does the graph f of x have an inflection point? If you don't remember what inflection point means, we'll look over on the board. That is when our second derivative is equal to 0 or undefined. And what else happens at that point? It changes signs, right? So the second derivative changes signs. So that's my justification. I just need to go find it. So if I go back up here, my second derivative is 0 or undefined at all of those marked places, 0, 0, 0, right? So at these 3 places, I need to look, is my slope changing from positive to negative or negative to positive on the left and the right? At this point, do we agree? Yeah, it's changing from negative to positive. What about this point? Positive to negative. What about this point? Negative to positive. Yes. So all 3 of those values are going to be inflection points because of that definition there. So at x equals -1, 1, and 2, f of x has an inflection point. Has inflection points, I should say. And that is because of our reasoning right there. It changes sign at that value, and the second derivative is 0 or undefined. One last graph of f of x, given this information that we've already been given about our derivative function, okay? And it has to go through the point -3, 0. So we can go ahead and mark that on our function, -3, 0. This is my graph f of x. Using my derivative function up top, okay? So if it helps you, it kind of helps me, I think, to write down the information that you know. Like I know my first derivative is greater than 0 on places on that graph. That tells me where it is increasing, right? I know where is my derivative less than 0. That tells me where is my graph decreasing on the graph that we were given for the derivative. I know when is my second derivative less than 0. That tells me where it is concave down. And when is my derivative greater than 0 tells me when it is concave up. Okay? So I would suggest writing those intervals for all 4 of those pieces of information, and then try and sketch a picture or a possible graph of what that would look like. Okay? I'm going to give you guys about 3-4-ish minutes to try that out. List all those things. Try and draw a sketch. I'd rather have it be totally wrong and you fix it than to just not do anything. Okay? So try it out. All right, hopefully you guys got those values as well. I'm going to go ahead and start sketching a graph. It starts out. Okay, so I'm going to start by drawing my increasing, decreasing, and then we'll check to make sure our concavity works as well. Okay, it has to go through that point of -3, 0. So it says we're increasing up to -2. So I'm going to go ahead and increase up to -2 here. And then at -2, what are we doing? Decreasing, okay? We're decreasing all the way to 0. So I think some of you just decreased here, but we could also decrease all the way down here. It doesn't matter where we end up on the y-axis at 0, as long as I'm decreasing there, okay? And then at 0, I am increasing until I get to where?
2.
To 2. So increase here. Ooh. Increase here. And then at 2, right, it doesn't actually exist, like at that point we have like kind of that inflection point there, but then it's still increasing 2 to 3. So instead of just going like, you know, like this, right, there needs to be kind of a change there, like a little S type change, something like that, showing that that point right there is an inflection point. Again, that could happen like up here. It didn't have to happen all the way down there, right? This is just a possible function, f of x. It is not probably what a lot of you had on your graph, okay? So this works for both of those. However, when I check, like you were just saying about this one right here, it is concave down from -3 to 0, right? It's concave down here. But then I also need it to be concave up from -1 to 1. So if we look here from -1 to 1, that piece is concave up, where like this point right here is kind of our inflection point. That should be at actually the -1 there. And then I need to change this to be concave down. So let's change this piece to be concave down at that point of 1 to 2. So let's go like this. Yeah, something like that. Ooh, wow. It's really hard to draw with my finger. Okay, something like this, where it kind of goes through. It doesn't have to go through actually that exact point. So let's go up here maybe. Okay, so starting here, it is concave down all the way up until we go to 3, which from 2 to 3 it's changing to concave up. Okay, so this piece here is concave down in yellow there, and this piece here in red would be concave up. Okay, if you're not sure on what your graph looks like, if you're not sure if it would work, you can ask me and I can check yours. But any questions on that graph that I drew? We good? Okay, the rest of the problems that are on these notes are just multiple choice questions. There's like a total of 8 to 10 of them. I would suggest trying a few of them out. They're basically doing the same sort of idea here, but it's just multiple choice. There will be a few questions similar on your test where you look at a function f prime and tell me some things about, is it an inflection point? Is there, you know, concave up? Is it increasing? And be able to tell me kind of those intervals and stuff. So try a few of those out. I'll post the answer keys for those, as well as there's already an answer key posted for your homework. Okay, sound good? Let me know if you guys have questions, please.